I'm going to carry this around.
Hello? Yes, okay. I'm going to preface this by saying that I know next to nothing about functional reactive programming whatsoever. I don't really know what it is outside of what I've picked up by Conal yelling at me on Twitter, and you know what I learned in Eric's talk. But the good news is that a lot of this stuff that's in my slides is very coincidentally touching on a lot of the stuff that Eric talked on in terms of like the names that you'll see and some of the concepts and ideas. If you want to bridge the gap between the two, just take everything that he said, replace the word signal with the word process, and you're pretty much done. So, but anyway, I have like way too many slides for a 30-minute talk, so I'm going to talk as fast as I possibly can, and maybe we'll get through everything. Scalaz Streams. Who here has heard of Scalaz Streams? All right. For those of you who don't know, it's basically a library for doing stream-oriented functional reactive programming-ish, sort of, in Scala in a really nice way. And I have no idea what I meant to do with this slide. They are somewhat unique in terms of streams in that they're done via a pull mechanism. So what does a pull mechanism mean? Well, let's talk about some of the stream things that I thought about when I thought of, well, what are stream libraries that I've heard of on the Google? And the Google says that there's Java 8 streams and there's Akka streams, and there may be others, but I don't know about them. And Java 8 streams and Akka streams both operate on a push model. So data kind of comes in and it gets shoved into your stream, and you have this way of talking about like how events are going to work and like what's going to happen as events flow through this thing. But there's essentially an outside source that just sort of jams these things down your throat. And this is very natural and intuitive for a lot of things like, say, responding to something that's coming in over a network, right? You know, some outside source, outside your machine, perhaps outside your continent, is jamming data down your throat, and you have to do something with it. So that's very nice. But it does have some problems, right? And we'll talk about those in just a second. Akka streams work in a very similar way. In fact, they're trying to unify the APIs a little bit. So these are what people try to call like reactive streams, reactive, and nobody seems to be able to define that word. So because they can't define that word, I'm going to coin the word co-reactive, and I'm going to say it describes these things. So co-reactive streams are like Ed Kmet's machines, okay? And Ed Kmet's machines is a Haskell library for doing functional reactive programming, one of the 500. And it basically inspired, but did not directly port to Scalaz Stream. So Ed Kmet was the guy, brilliant guy, one of the most prolific open source developers on GitHub, like ever, came up with this idea for functional reactive programming in Haskell. It's a really neat library, but it's very nascent. It doesn't do a lot of the things that you would want. So Paul Chusano took this and made it something useful, made it something powerful, and more importantly, made it something that's actually very intuitive and easy to work with. He took these very complex ideas and distilled them down to something that's actually very straightforward and very easy to understand, both from a low level and a high level. And so I have a ton of respect for what he did with the Scalaz Stream project. So push versus pull. Like I said, push is like someone outside your universe jamming events down your throat. You have to worry about handling them, right? It's assertively pushed into your data flow. And the thing that you should kind of hang your hat on with this is that when you have push-based streams, it's very easy to take a stream and sort of dump it into multiple places, right? Because you have this series of processors that's working on your stream, and events are coming in, and you can just very easily like take those events and copy them off in various places, right? Because they're just coming through and flowing through your data flow. And that's, you know, it's no problem at all. But multiple input is a little bit harder, right? So it's hard enough to have one person jamming something down your throat, but you have two or more people, and then it gets to be very complicated and messy. And you see this in Java 8 streams, for example. If you try to build a stream in Java 8 that merges things from multiple sources, it can be a little touchy. You can do it. You can do everything with it, but some things are harder than others, and there's more gotchas. Pull-based streams have the opposite problem, right? So what you do with a pull-based stream is, rather than having someone at the front of your line, like pushing things in, you have someone at the bottom that's just sort of turning the crank, right? Pulling things out one at a time. You're like, I want the next element, and the next, and the next, and the next. Someone at the bottom, at the end of your pipeline. And this is really nice, because it means that you can pull from multiple sources very easily, right? So at the end of the day, right, someone's pulling down here and way up, winding up here. You can very easily pull from this guy or this guy or this guy, and that's no skin off your nose. It's very easy to do. But it's very hard to have like multiple people pulling on you simultaneously, because then you have this question of like, well, do I give the same element to both people? Do I hang on to one of them for a certain amount of time? I don't know. Those things are hard. So those are like these are kind of the trade-offs between push models and pull models. And again, you can do everything with everything, but some things are easier than others. With push streams, you have to worry about back pressure. This is kind of the most obvious thing that I think of when I think of push streams, is you have to have some mechanism for slowing down the guy who wants to ram things down your throat. Just a quick prelude. Does everybody know what back pressure is? Everybody knows what back pressure is? Good. All right. I'm going to assume everybody knows what back pressure is. Back pressure is really important. If your application doesn't have it, you're doing something wrong and your servers are going to explode. Go check to make sure your servers haven't exploded yet. So with push streams, you have to work really hard about back pressure, because you have to actually tell them to slow down or have some mechanism for throttling what they're pushing into you. And that can sometimes be very difficult. It's like an extra step. With pull streams, that's not even an issue, right? You have someone pulling down at the end of the world, right? Someone's turning the crank. And if it takes you a little bit longer to give them the next element, well then clearly it's going to take you a little bit longer to pull the next element from the source, right? So back pressure happens by design. Back pressure is definitional in pull-based streams. And that's really, 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 really nice. The downside is, and perhaps upside, depending on Eric's perspective, it is declarative control flow. It's very, very declarative as opposed to the push streams, which tend to be more imperative. And that can lead to some very confusing corners. I'm going to try to help you avoid those corners, because I'm assuming that you're going to want to go out and try Scalaz Streams like right after the talk. But they still exist, and they're very hard to work around sometimes. So, some conceptual foundations. There's two main things that we need to understand in order to be able to work with Scalaz Streams and be able to understand kind of examples about what they're doing. One of them is task. So task is something that's in Scalaz, which is a functional programming library for Scala. And it's basically like Future. So if you're familiar with Future from Java, or probably more usefully from Guava or from Akka, task is a lot like that. But unlike Future, task doesn't start executing things instantaneously. And even more importantly, by virtue of not starting executing things instantaneously, it doesn't leak memory. So this is a really nice property, surprisingly enough. So task is like a better Future in a lot of ways. It has some weird corners, but it's very, very nice. Process is our main abstraction, right? This is the thing that it's our signal, it's our source, it's like whatever you want to call it. It's basically, though, at its simplest level, it is a strict sequence of actions, okay? So I was talking about like someone is turning the crank and asking for the next thing, and the next thing, and the next thing, right? That thing that they get is an action, right? They get the next thing from your stream, from your process, and that thing is a task, which, they run. And then they get the element that's inside of it. So process is basically just a sequentialization of all of those tasks. And that is a surprisingly, profoundly powerful abstraction. So task. Task is fully lazy. When you create a task, it does not start executing right away. This is really, 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 really important to remember. And it means that you no longer have to worry about creating your futures in a particular order in order to get some sort of concurrency, because that's an incredibly insane thing to do. Creating a future executes instantaneously. If you create a future and you put some code into it, it gets scheduled and it's run. And it's awful that that happens, because if you think about it, then it has to do things like memoize the result, never run it again, hang on to it in case you might ask for it later. And that just sounds like a recipe for disaster. I've had so many bugs that come from this, and I mean, I'm sure all of us who've worked with futures have had these bugs, whether we know it or not. Because task is fully lazy, it's really easy to move it around between thread pools. It's very easy for me to describe a task and then later on say, oh, I want to run it on this thread pool. Well, I might also want to run it on this thread pool. Let's try running them at the same time. No, that's okay. Like all of that stuff is really, really easy. So when you have certain thread pools that need to be used by certain modules rather than other modules, that's super easy to do. You get better thread utilization being a fully lazy feature because it doesn't demand that you schedule things on a thread pool. So unlike Future, where every time you have a sequentialization of the next step in your future computational chain, it has to go back to the thread pool and dump stuff on the blocking queue and like come back and reschedule things. Task doesn't do any of that. Task just says, oh, we're going to move on to the next thing. and it just uses the thread of execution that it is currently on. For those who understand this term, task is a free monad. For those who don't understand that term, don't worry about it. It just basically works the way you would expect it to. One thing that is unintuitive about task, though, you have to be explicit when you want parallelism. And I will show you exactly what that means with the classic naive Fibonacci example. So here's a Fibonacci example that runs inside task, right? So we have our standard function thing that takes an integer, and we case on that, and then in the recursive case, we call fib, and we call fib, and then we flat map on this, and yield the result of adding them together. And that gives us a task of int, which we run down at the bottom to actually get our result. Normally you don't run tasks very often, because this is the bad thing to do. It's like calling get on a future. But there's no parallelism here. There's no concurrency whatsoever. Because we have in the middle, we have get the fib for n-1, and when you're done doing that, get the fib for n-2. So where we want parallelism, naively, is at that point. We want to do those two simultaneously because they're independent on our incredibly, incredibly naive implementation. And the way we do this is with this incredibly verbose garbage that you will never have to worry about. Basically, we create an instance of something called a non-determinism, and we say, hey, do these things both at the same time and give me the results. And whatever you want to do, run them as fast as you possibly can. Again, this is not stuff that you have to write very often, by which I mean basically not at all, because process takes care of it for you. But it's good to understand that this stuff is explicit. Explicit parallelism. You always know where your concurrency is, and so you can't have like bugs that sneak in randomly with things surprisingly executing out of order. I said it was really easy to shift things onto a different thread pool. This is how you do it. You can take a task, here's a function that takes a task of any type, and it puts it onto my thread pool. It moves it over onto a different thread pool. That's a very easy thing to do with task, and it's actually very hard to do with future, because future is already running. By the time you have a future, it's already running on some thread pool, and that's really scary. By the way, this idiom is so common, there's actually a special function for it on task called fork, which doesn't behave anything like fork in C. Another thing that is super, super cool about task, and this is one of the #1 reasons to use it, I think, is you can take any callback-based computation and you can turn it into a task. So anytime you have something that's like an event listener or an event handler or some sort of on-complete callback, any of those things, you can treat it like a future using this interface. This is hilariously, insanely, magically powerful. I can't even describe how wonderful this is. But basically what we're doing is we're taking a future here, which happens to be a Scala future, and we're saying, oh, I want to convert this future into a task without blocking on the result, without shifting thread pools, without messing up any thread utilization at all. I just want to treat it as a task. And wham, there it is. Use the async thing. I can explain this code, but it's not important. Just know that this function is there, so you can find it if you need it. That's the exciting stuff. Okay, process. As I said, process is an ordered sequence of actions. You ask for an action, and then the next one, and then the next one, and then the next one. And then, as I said, back pressure comes through the fact that if you can't ask frequently enough, things just slow down, which is really nice. It's very easy to merge things. Like I said, you can just ask for data from one side or the other. So it's very easy to put streams together in this respect, whereas push streams have a harder problem with this. And just like task, you have very, very explicit parallelism. You say, hey, I have two streams, I want to put them together, and I want it to happen sort of non-deterministically, right? You have to be very, very explicit about that. But mercifully, thanks to heaven's wisdom, it is much less verbose than what we had to do with task. Anyway, let's look at some examples. So in order to support these examples, we're going to need this tiny little utility function here. You don't really need to understand this, just kind of understand that it's happening, right? So this is a function that takes a URL as a string, because that's cool, and returns the contents of the web page that's pointed to by that string, but apparently only if it's under api.stuff.com, which is apparently a URL. It's using the data binder dispatch library, things are in there, and then it uses that future to task function that we had before. But the point being that it gives us a task that goes out and fetches a website for us, which is very nice and very helpful, and we're going to take advantage of that momentarily. So here is a simple example of some processes. We have a process at the top that's just a static range of numbers. It counts up from 0 to 9, inclusive. Gives us those numbers, and then we have these standard sort of collection operations on them, right? All of the things that you would normally do with like a list or a vector, in Scala, like they're there. You can map, you can filter, you can flat map. All of those goodies are there and you can use them. Down below, we have the val pages thing, right? We take adjusted, which is this thing that we pointlessly twiddle our numbers for, and we flat map on it, and then we take the number, we call the fetch num thing, or we call fetch URL and say, okay, give me the contents of this web page. But because this is a flat map on a process, we have to return something that is a process. So we use this process.eval function. What that says is, okay, I have a task of A. I want to turn it into a process of A that just gives me that one value. I don't care, it's going to be a process that gives me exactly one value and then stops and shuts down. But that's all I care about. And it gives me that value by running this task. It doesn't run it immediately, but it will run it when I ask for it. That's what the process.eval function is. So you can think of it like lifting a task into a process. Very, very, very useful tool. We're going to use the heck out of this. So pages is a process that under the surface gets all of these numbers and then goes out and fetches web pages for us. But it still isn't actually running yet. None of this is running yet. We're just describing what to do. And what we're going to do down below is say pages find contains Waldo. So we're apparently looking for Waldo in the contents of these web pages. And once we find one, we're done with it and we're going to print it out with this found to IO stood out lines thing that was very inspired by Haskell. I'm going to explain what this whole to IO thingy is. We're going to talk about that later. Just treat it as magic witchcraft right now. It's basically just printing out the contents of this stream. And then what we do is we run the stream. So when you run a process, it doesn't actually run it yet. Confusingly enough. I wish they'd called the method compile or something like that. Because what it does is it takes the process and it turns it into a task. And that task is like, hey, run this task, and I will do all of the work you described in the process which originated me. But only when you run this task. So you still have full control over when things are scheduled, when things run, whether they run at all, and what your utilization looks like. I said it was really easy to merge processes, and indeed it is. So here's two processes. nums1 and nums2, describing completely pointless ranges of numbers. And we can put them together by interleaving them. This interleave is fully deterministic. Remember, we have to ask for non-determinism. We have to ask for concurrency, and we're not going to get it if we don't ask for it. We're not asking for it here. We're saying, hey, this is how you're going to describe the nums process. When someone asks you for a value, take one from the left side. The next time they ask you, take one from the right side. Then the left, then the right, then the left, then the right. So of course you're waiting for things here, but in our case it doesn't actually matter. Here, however, is an example of where things can be a little bit confusing. So we're using the interleave function again, but here up at the top, the source of the original process that we define is defined by this task that reads from an atomic integer. This is a Java util concurrent atomic integer. And we define this process that evals that task and then repeats it, right? Takes the same process and runs it over and over and over and over and over again. So source, right here, is our first infinite process. This is a process which will run forever, grabbing the current value from the atomic integer, over and over and over and over and over and over and over again. And then what we do is we have a left side and a right side that are derived from source, they print out, or they convert those values into strings, and then we put the left and the right back together again. So here we have a single process that splits apart on two sides, and then comes back together again in the middle. So this is both the multiple output and the multiple input. Does anyone see what is horrifically wrong with this example? Where is the problem going to be? Okay. The problem is the output looks like this. Unlike what you might expect, the left and the right sides are not actually getting the same values because they're both independently running that task. They're both asking for the next value from the atomic integer. There's no sneaky memoization going on here. There's no like magic values being cached and handed off to other references to things that you might not know about. None of that is happening, no memory leaks to worry about, but it does mean that this sort of thing happens. So the situation is basically this, right? We started off with one process, we split it into two, we derived two different processes from it, and we brought it back together. But from the perspective of Scalaz Stream, we didn't start off with one process, we started off with two copies of the same process, right? And Scalaz is just going to run them completely independently. It's not going to try to coordinate between them at all, because from Scalaz's perspective, it's two different things. This is a very, very, very obvious thing. I've showed you how to get from an atomic integer. What is a really, really useful pattern is to be able to build a process that reads from a blocking queue, right? we work with concurrency, we therefore work with blocking queues. All of the time, blocking queues are really, really important. So how do we do this? Well, array blocking queue. Standard Java thing. Array blocking queue of message that has size 10 because I'm afraid of things. We're going to write a task that pulls the value out of the array blocking queue in a blocking fashion. And note that I'm not afraid to do this. I'm not afraid to block this thread and say, hey, I want this value from the queue, and if you can't give it to me, tough. That's okay. I don't have a problem doing that. And then we create a process that simply evals that task, right? I said we were going to use the heck out of this. And then I want to keep getting values from this queue as long as the queue is able to give me values. So we just repeat this process over and over and over again infinitely. This is how you get things out of a queue. And this is actually such an incredibly common pattern that there is a utility in the Scalaz Streams library for doing this in a cleaner way. It's just called blocking queue. So you say async.blocking queue of type message, bound of 10, and then give me the DQ side of that. I can get the NQ side of it too, but I want the DQ side of it, and I want you to just pull stuff off of the queue for me. And this also gives us some other nice tools, like the ability to stop the queue at some point. Async blocking queue is the bee's knees. I use this everywhere, all over the place, all the time. It's the best. So we've seen how to get data into Scalaz Streams, right? Which is to say, we've seen how to define sources of data, data flowing in. Well, sources of data aren't very useful unless you can send that data somewhere on the output side, unless you can pipe it out somewhere, and that's where sinks come in. So data has to go somewhere. Where does that data go? Well, you might want to write it out to an NIO channel, you might want to write it to disk, you might want to write it to the output stream, or you might want to do all of those things all at the same time. And it's very important that we can support these use cases, because otherwise, Scalaz Stream is just something that you put a bunch of data into and you never really get results out of it. So the question is, well, how do we define a sink? How do we make this work in this nice framework? Because remember, process is kind of this really nice abstraction, right? All it is just a sequence of actions, right? And the next action, the next action, and the next action, and the next action. Where do sinks fit into this picture? Well, sinks fit into this picture as a stream of functions. And this is really, really, really beautiful. So this is the type of sink. And if you think about parametricity, this actually answers exactly what sink does. And don't worry about the scary word. It basically means, okay, a sink is a process of a particular type. So a sink of task is a process of task. But instead of containing values of type A, it contains functions from A to task of unit. So that means that if I have a sink of int, that means that for every int I want to give it, it can give me a function which will eat my integer and give me an effect, a task of unit. And I can run that effect to, I don't know, put my integer on a channel somewhere, or put my integer to the output stream. That's what that will do. And it will just keep giving me one function for every single element that I want to give it. So this is how sinks work. And there's a lot of really wonderful utilities inside of the Scalaz Streams library for working with sinks that take on this form. You can map over them and glue them together with streams and things like that. So how does that work exactly? Well, here's how we can create a sink, all right? So at the top we have a function called write. Write takes the string, returns the task of unit. So this meets the criteria for what we want to do with a sink. Remember, we have to create a function from A to task of unit. By the way, I didn't actually explain it, but this task delay constructor, this is different from the task now that you saw in the Fibonacci and the task async that you saw in the future converter. Task delay just basically means the stuff inside the curly braces, run it whenever you're run, but not now. Not before you're run. Just run it when you're run, and that's all it means. Just bottle this up, run it later. So task delay, print line string. Very, very obvious thing to do for write. We create the sink by using this process constant thing, which that's basically the same as doing the eval repeat thing that I did before. But this is another one of those utilities, right? So this is something that, like, it's a very common pattern to want to take a single value, put it into a stream, and just like keep getting that value over and over and over and over and over again. Because it turns out that there's only really one way to write to standard out, and I don't want to vary it over time. So there we go. We have an infinite stream of write functions. How's that? And we create a static process down below it called source that's a range of integers again, and we map those integers to strings. So now how do we send those strings to the standard output stream, to this sink that we have? Well, we can use zip. Zip works exactly the same way that it works on collections. We zip together the source and the sink, which gives us a single process that has pairs inside of it. On the left side of the pair is the value, the string. On the right side of the pair is the function that will take the string and perform some effect. And this is exactly what we see inside the pattern match, right? We take apart the pattern match, we have a string and we have a function, and we call that function on the string and wrap it up inside of the single process, right? So this is how we can send values from sources to sinks. Very straightforward. We can actually use this to send values to multiple sinks very, very easily. So here we have two sinks that we're pretending to create, one for standard out, one for some sort of hypothetical NIO channel, and we're just zipping them all together, right? Source, zip, standard out, zip, channel, put them all together, have this giant pair inside of our thing, flat map over it. Huzzah! This is so composable and great, and it's incredibly confusing, and I would never want to write code like this. The good news is that this pattern of zipping together your sources and your sinks is so common that there are actually some nice functions for doing it. And they're called observe and to. So the to function in particular, the to function we saw earlier, and I said just treat it as witchcraft. Well, it's not really witchcraft, it's just zip. The to function takes a source and a sink, like say IO stood out lines, and it zips them together and invokes the function and gives you the stream of effects. So it actually represents dumping your data, dumping your stream into some sort of sink. Observe is really nice in that it allows you to dump something into a sink without actually losing those values. So you can dump data into the sink, but also dump it to another sink. Or maybe dump it into a sink and sort of process it and go along and do other things. This is profoundly useful when you want to debug your code. So every time I work with Scalaz Streams, I have to like sit there on the stream and print out code because I have no idea what the heck is going on and what values are flowing through. Observe makes that so easy because remember, observe is marrying a source to a sink and then keeping the original values that are in the source. So no matter what the sink does, I still have the original values. So I can write this debug function that takes a process and returns that same process externally unmodified. Like there's basically nothing that has changed about here. It's not going to affect any of the semantics of my code. All that's happening is as the process eventually evaluates, it's going to print out the data to standard out with this debug prefix. So I use this all the time for logging. And it's like incredibly easy to do because I can just throw this debug function around whatever stream I'm interested in, and all of the code will still work and all the bugs will still be there, but I'll be able to see things logged as they evaluate. So that's really great. So concurrency. Streams are really important for concurrency, right? This is one of the motivations for having them in Java 8. So if we can't do concurrency with Scalaz Stream, then sort of the question is, why are we doing this at all? Well, concurrency with Scalaz Streams is, as I said, always explicit, okay? You always have to ask specifically, hey, I want this to be parallel. Hey, I want it to be parallel in this exact way. We don't want bugs creeping into our code by mistake by the library magically trying to optimize something that it really shouldn't be optimizing because it doesn't understand what I'm doing, right? We want to ask for it when we want it. We're smarter than the library, and let's take advantage of that. So we have to be explicit about parallelism, and there's two different ways in which we can do it. So one way that we can be parallel with streams is just take two streams, glue them together, and race them as fast as we possibly can. Take two streams, A and B, fire the starting gun, and as soon as they give us a value, just put it into our output stream. But whoever's giving us a value faster, that person's going to get more values faster into the output stream, right? That's sometimes a very useful thing to do, right? Sometimes you just don't care about who's running faster. You just want to get them together as fast as they can possibly run and maximize your CPU utilization. The second form of parallelism is what I like to think of as turning a stream sideways. And this is basically like, well, I have a whole sequence of things, right? I want to perform some computation on those things, and I want to chunk it up such that, you know, each chunk of like 4 or 5 things, those run in parallel, and then I just sort of zip my way down the stream. And I have a diagram which makes this a lot clearer. Almost everything is implemented on top of this fancy combinator that's called Y. And that is how you pronounce this. It's a completely forgotten term from railroading, but it basically does all of the parallelism heavy lifting under the surface. You don't have to use it directly 99% of the time, but it's good to know that that's how it's implemented because sometimes you just need to look for stuff, and this is where you look for Y. So how does this work, right? How does the racing thing work? Well, we have two streams, like I said. We use y, and we can put them together like this. And one stream is getting things in faster than the other, and then that stream kind of slows down, and the other one is able to get things in faster. Like, it's just a data race, right? But sometimes this is fine. Sometimes this is what you want. Actually, a lot of times this is what you want. So if these two streams are producing values that are of the same type, well, I'm just going to try to run them as fast as I possibly can, and they're going to give me values as soon as they can. And this is very, very easy to do. So we have a left stream and a right stream. They're completely independent. I don't care where we're getting them from. Maybe from the network, maybe from, I don't know, some complex thing. And we can merge them together because they both produce type message. And we do it with this left.y, right, y.merge convolution thing that actually has a utility that you don't really have to worry about that. So this merge function here merges left and right, and it compiles down to the same thing as the .y, right, y.merge thing, but this is the syntactic sugar and it's much nicer. I really, really wish this were called race, because that's really, really what's happening. It's just running the left and right as fast as they possibly can go, and stuff. By the way, for those of you who are still thinking about back pressure, because you should be, there is a bounded queue inside of here that prevents one stream from getting too far ahead of the other and overflowing your memory, right? Because that's actually a serious problem. Okay, well, what about if we have streams that have two different types, right? Maybe if we're not merging two types of messages, maybe we're merging like messages and lines or something like that. Well, we could do that too. We just need a different way of thinking about it, right? So here we don't want to just jam all the data into the same stream and not process it. What we want to do is we want to put it into something called an either. So either is something that Scala has in like various incarnations. It's in the Scala standard library. Scalaz has a slightly better one that it's a little bit easier to work with. And because Scalaz is Scalaz, it's represented by this // thing that you can see there that's very scary, and I'm not going to talk about it at all, but it just means either. Sorry, that's Scalaz. It's not scary, it doesn't do anything weird, it's just an either, right? So it means that, okay, this is a process, and for every element in this process, it's either going to be a message, or it's going to be a line, but it's not going to be the two of them at the same time. So we then merge these two streams together with this either combinator, which again delegates down to y. And this either combinator says, okay, run these two as fast as you possibly can, and if you get a message, put it on the left side. If you get a line, put it on the right side. And that way we can tell them apart and make some computations later on down the line. This is super useful. And there's a whole bunch of utilities actually in process for dealing with processes that have ethers inside of them. So that's really, really powerful. Okay. So useful whys to remember. Like when you're using Scalaz Stream, it's good to know the tools that are out there so you know where to look because the documentation is terrible. Useful whys. Y.merge. Glue things together, race them as fast as you can. Y.either. We already saw that one. Y.yip has nothing to do with dogs. It's basically the same as zip. It's just like a non-deterministic form, right? Okay, zip, but run these two sides in parallel instead of running them sequentially. Most of the time, that's what you want to do anyway. There's also drain L and drain R. That means drain left and drain right. It means, okay, I have two processes. I want to put them together. I want to run them both, but I only want results from one side. These don't work. These are bugged. I have no idea why they're buggy, but they really don't work. Don't use them. Not even in the latest release. Okay, so we've talked about racing streams together. How about turning them sideways? What does that even mean? Well, it basically just looks like this. We have one stream, it's got a bunch of stuff in it, and we want to perform some computation on this that is like, doing the same thing but across multiple elements simultaneously. This is just for like processor utilization stuff, right? So we want to have a way of turning it sideways and then collapsing all of those things down together into some sort of chunk that we can then process, right? When we process that, then it shrinks down into this nice collapsed stream that's much faster, and the animation was cool, and I was bored this afternoon. So how do we do this, right? And what does it actually look like? Well, let's think about the example of our fetch URL thing. Remember I had that from earlier where we had this stream of web pages, and we wanted to fetch those URLs? Well, because it's a sequential list of actions, right? The way this is written right now, it's just going to fetch those URLs one after another after another. And that's very inefficient because maybe some servers are slow and maybe some servers are fast. Well, it would be much better if we could turn those URLs sideways and sort of chunk them up and like fetch 4 at a time, and then fetch the next 4, and then fetch the next 4, and do it all in parallel. And you can do this with a couple of different tools. Gather is one of them. So here we say gather 4 things at a time. Get 4 things from the stream, run them all in parallel, and then, you know, move on and do the next 4, and the next 4, and the next 4. It takes a value that tells me how many numbers that I should grab all at once. So this is a value that you should probably set to like num processors or something like that. The last chunk of the stream, as you would expect, is something that it would truncate. So it's going to grab strictly 4 elements, and then 4 elements, and then 4 elements, and then it runs out of elements, so it just grabs the last 2, and then it's done. This is fantastically good if you have a stream that is of finite length, right? You only have 7 things in it, I'm just going to chunk it all up and do this. It is terrible if you have an infinite stream. Do not use this for the love of God. This is a really dangerous function. I lost so much time to this. Because what happens on an infinite stream is it sits there waiting, and it's like, I want the 4th element, I really want the 4th element, give me the 4th element, come on, and it won't truncate at all on an infinite stream. That's really bad, because it literally will deadlock your program. So especially don't use this if you source from a queue, which is a really common thing to do. What you should do instead is use something called merge-n. This was called merges in Eric's talk. And merge-n takes a process of processes, which is this fancy pages thing up there that I gave you the type for, right? It just basically means I have a stream that will give you a whole bunch of streams, and then inside those streams is some data, right? These are things that we can talk about. It takes a process of processes, runs them as fast as it possibly can, and you know, doesn't have any bounded sort of chunking thing that it's going to try to do. It's just going to be as opportunistic as it can about running things fast. So merge-n is almost always what you want when you want this sort of parallelization. It is a little strange to use because you have to worry about this whole process of processes things, like, I don't know, that's weird. It uses a variable bounded queue, so that's sometimes good and sometimes bad. Like, you have to think very carefully about back pressuring your performance characteristics. But it is generally what you want in terms of racing them, right? It races all the input streams up to n, which is a parameter that I didn't give. And when you want parallelism with stream, and you're not racing 2 streams against each other, this is probably what you want. So I have 3 minutes left to do my grand finale example. So be ready for fast talking. I'm going to build a chat server in 2 slides. A chat server that runs on top of Netty. How many people have written something on top of Netty? Okay, it's a really good application. Was it a pleasant experience? Did you come away from it being a JBoss evangelist? No, no one does. Netty is awful. Netty is a terrible framework. This is not a terrible framework, and I can wrap it up inside Scalaz Streams, and it's beautiful. So I have this wrapper, Scalaz Netty. I hope to open source it soon. Cross your fingers. But if you can't use Scalaz Netty, you can use Scalaz NIO, which does exist, and it's in the Streams project, and it works just fine. I also use scodec. I'm not going to talk about what scodec is. Google it. It's amazing. Everyone who uses Scala should be using scodec. Period. Stop. And I'm going to demonstrate the power of the process abstraction. Is Chris going to kick me out? Okay. Okay. You looked like you were preparing to
no.
calm me down.
No.
All right. So let's think about what the server is going to do in a chat server. What does a chat server have to do? Well, it has to accept connections as fast as they come in, nominally, right? I mean, you have to be a little bit careful about resources. And you want to be able to process those connections in parallel. So these are things we have to think about, right? Process those connections in parallel as fast as you can. Any inbound data we want to take and we want to put it into some sort of relay queue, right? So we can take that inbound data that came in from the client and pass it off to every single client. Basically just reflect it all back in some sort of multiplexing way. And we simultaneously also want to do the other side of that, right? We have to reflect it back, so we have to read the queue that we created and pass it back to the channel from the client, right? I put this including all history bullet point in here before I realized that everything on this slide was mostly wrong. Sorry about that. Ignore that bullet point. And we continue doing this until the client decides it wants to stop. So the server's not going to proactively close connections or anything. It's just going to sit here and reflect data back. So what does this server look like? Well, it really only looks like this. It's very, very, very straightforward. So we have an inet socket address, which is just a Java thing, right? We get that from somewhere, maybe a config file. I don't care. It's question marks. And then we have this relay topic. This is another one of those utilities that's inside of Scalaz Streams. And this is basically like a queue where you can have multiple subscribers. So whenever you subscribe to the queue, all of the subscribers that are currently on the queue get the same data all at the same time. But it doesn't hold on to old data, right? So if you have no subscribers, the data is just dropped. And you can publish to the queue as many times as you want. So this is exactly what you want, right? It's a many-to-many sort of reflecty thing, right? And this is a very common pattern in server-side programming. So here's our server, right down in the middle here, this handlers thing. It says netty server address. This is how you connect to a server in Scalaz netty. It's like 700 lines shorter than the netty examples. And we map this, and we get a client out of it. So with every connection, we're going to get some sort of client abstraction, which I'm going to tell you right now is a process. And we dig into that process and we get out something called an exchange, which is basically just a pair of a source and a sink, right? So we have a way to get data from the client, we have a stream of data from the client, and then we have a stream that we can dump stuff into that feeds data back to the client. Exactly what you would expect from this sort of situation. And then we say, okay, your input stream, I want you to send your data, any data that the client gives me, put it in the relay, and any data that the relay gets from its subscriptions, I want you to dump it into the sink. And then merge those two streams. So just run them as fast as you possibly can, do them both at the same time, because I don't really care about any of the output, we're just going to yield unit at the end of the day. And that is our entire server. The only thing left is to do the run everything in parallel bit, right? Accept multiple connections simultaneously. Well, we do that with merge n. So our server gives us a process of processes, right? It's the outer process is the server, and the inner processes are the inner clients. Well, we just mapped those inner processes and said, well, for every client, do this thing. Well, now we want to say, I want you to run as many clients as you can possibly do all at once, right? Within some bound, but run as many as you can possibly handle simultaneously on this thread pool. And that's what merge n does. So this is our server. This is it. We could run this in a REPL and it would work. What does our client look like? Well, our client has to do the following things. It has to establish a connection to the server and maybe do some sort of handshaking thing, but we're not going to do that because we're cool. We want to pipe standard input to the server so that users can type lines that are unprompted, just like old telnet style. And we want to transcode as UTF-8. Pipe the server response back to the standard output, and then keep going until someone control sees us, because that's how everybody wants to exit their applications, right? So this is the chat client. Very, very straightforward thing. We are, however, going to need this utility function. So this utility function here, I promised I wouldn't talk about scodec, and I'm not going to talk about scodec, but this is what it's doing. It just converts an exchange that works in terms of bit vectors, which is just basically byte buffers, right? Converts an exchange that works in terms of byte buffers to an exchange that works in terms of strings. And it's actually cool that it can do that in that little time. You can actually do this with zero copy transcoding and all sorts of other really fancy stuff on top of direct byte buffers, but we're not going to do that right now because no scodec. Client. This is the entire client. So it's even smaller than the server. We connect to the address. Netty connect, address. This is like 400 lines shorter than the netty examples. And we get an exchange out of that, just like we got on the server side. So again, unlike the netty examples, the server code and the client code kind of looks exactly the same and uses the same idea, so you don't have to learn two different frameworks. We transcode the raw data that comes from the client because we want to work in terms of strings. Remember, magic scodec function that everybody should be Googling after the talk. And then we pipe the output from the server to the standard out. We pipe standard in to our sink to send it back to the server, and then we just run those things as fast as we possibly can, yield unit, and we're done, and this is the entire client. That's it. This is the entire client. So things about this that are really cool. Number one, no resource management. None. Process has inside of it a way of understanding when the process has been terminated. You cannot leak resources unless you do something evil, like take a value and like put it in some sort of variable outside the bound. So I didn't have to worry about closing connections, I didn't have to worry about exceptions, I didn't have to worry about all the terrible, terrible stuff that happens with networking. All of that was taken care of for me asynchronously on a thread pool without blocking operating system resources. This is fantastic. And I did it keeping all of my application logic completely isolated from the networking logic, because the networking logic was hidden inside this stream abstraction. It's pure, I can reason about it, and there's no kind of crazy bugs related to closing the stuff or any terrible things like that. Back pressure just works with this. Like, I didn't even have to do anything special. Like, the server will throttle itself. Sort of, kind of, hand-wavy, topic. So topic is unbounded. You can actually have like as many subscribers as you want, which is sort of like accumulates data. That's kind of scary. It actually has an unbounded queue inside of it. You could write a topic that was bounded, and I really think they should, but yeah, that would be easy to do. But the rest of the back pressure just works. Just don't DDoS my REPL. Anyway, handshaking would be really easy. How many people have done handshaking with Netty? One. You live to tell the tale. Handshaking with Netty is awful. It's amazingly terrible. I have no idea how people thought this was a good idea. Here, all we would have to do is insert another line in that fork comprehension. And then on the server side, like after we get the exchange, just say, oh, do some stuff with this exchange and make sure that it actually worked. And if it didn't work, close down the connection. And on the client side, do the same sort of thing, but the client side half of the handshake. And it would just be in the same fork comprehension. It would be really declarative and easy. It's like, get the connection, do the handshake, do the prelude to the handshake, okay, now we're done, and actually run your steady state server stuff. Clean up your resources, be done. That's easy. It's incredibly easy and declarative. The client and the server logic looks almost exactly the same. It's really easy to reason about. So, I'm running really late on time, but we have a conclusion. We made it to the end of the talk. This is a different take on, quote, reactive, whatever the heck that means. I don't even know, but it's good. I like Scalaz Stream. It's helped me so much, and it's fast, and it works at scale. And I really, 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 really recommend that you use this. This is one of the best reasons to use Scala, in my opinion. Purity. Eric talked about this, and he kind of like waffled on whether or not it was a good thing. I am more dogmatic than that. Purity is a good thing. Purity helps me understand my code. Like, I'm not religious about it. I just care about like knowing what my code does. And purity helps me do that. Honestly, it's much, much easier to look at your code and find bugs this way and test your code, and it's just no puzzling about resource leaks or state or anything crazy like that. Scalaz Streams. You have actually seen 90% of the Streams library in this talk. Nothing else about it will surprise you now. You've seen it. And the stuff that you haven't seen, you can basically derive from what I've given you. This is the entire library, but it gives you these powerful tools that scale to very hard problems at a very high level of load. You basically know everything. So I'm super, super over time, but are there any questions? Yes?
Most of that looked like, thanks. Most of that looked like you could have implemented it in fairly straightforward Scala. I'm wondering if the Scalaz is just because that's what it's implemented in, or if there's specific Scalaz stuff apart from the ether.
So the implementation of Scalaz Stream doesn't depend on Scalaz very heavily. It's not using anything crazy like Kleisli or Profunctor or any of those things that I don't understand. It's actually, it is very straightforward Scala, as you said. What it does take advantage of is some things like ether. It takes advantage of monoid and monad. It takes advantage of non-determinism and task, which are both in Scalaz. So it's built on some things that Scalaz gives it just from a utility standpoint. But it's not, it's written in a very easy way. The source code for Scalaz Stream, outside of the Y stuff, which is crazy, the source code for Scalaz Stream is very easy to read. And it's a really good way to understand the framework.
All right. Well, thank you very much, Dan.
Thank you.